Alright, I think it should be ready now. Alright, so anyway. Hi everyone, this is Alfred from Nerd of Passion and welcome to the third live stream lecture. Okay, so time passed really fast, so before I know it, I'm already giving my third live lecture, so I hope you guys have been enjoying the lectures so far. So the previous two lectures, they are all recorded, so you can just catch them into my YouTube channel. So anyway, so for those of you guys who are watching this right here, right now, just want to say a big thank you. This really means a lot to me, and for those of you who have missed this, don't worry about it. You can watch this later anytime you want. It's all recorded. Okay, so today's topic, I'll be focusing on calculus, which is probably one of the most useful areas in math and also one of the most fun area in math. Personally, that is also my favorite part in math, because calculus is where you take your problem solving skill up to a really whole new level, and it kind of like allows you to look at math from a really new pair of eyes. So you are looking at math from a very new perspective. Okay, so my goal for today is not really on how to do calculus, on how to apply all the differentiation rules, integration rules, and so on. I'll leave that to textbooks and classes, because in classes, that is what we do a lot. Rather, my focus for today is more on why we do calculus, on having a bigger picture view on calculus, so we can really understand the concepts behind a calculus. Alright, so for today's lecture, you can download the lecture handout down in my video description. You can just download it from my website, and I really highly recommend getting it, so everything is in there, where I explain everything in a pretty detailed manner. Right, so just let me fire up my PowerPoint slide. Okay, just bring this down here and just get this screen up into full screen mode. Yep, perfect. Alright, there we go. Right. Okay, so once again, the topic for today's lecture is on calculus, where I'll be going through everything, just giving a very kind of like an overhead view from differentiation all the way up to integration. Okay, so for those of you who are new to calculus, these two terms might sound funny to you, but later you see what I mean by these two terms. Right, okay, so just let me begin by saying this. So for those of you who are starting to do calculus or have already been doing calculus for a while, give yourself a pat on the shoulder, because calculus is a very big step up in mathematics. So your math skill have already been level up a lot, and you can congratulate yourself for that, and you can go impress your friend by saying, oh yeah, I do calculus. So impressive. Right, anyway. Okay, so I'll just give you a sense of direction in what calculus is all about and how calculus fit into the grand scheme of mathematics. Okay, so let's think back, when you were a kid, what is the first thing you learned in math? Probably counting, how to count from 1 to 10 and then up to 100 and then 1000. But I think in reality, nobody really counts up to 1000, but we know how to do it. It's very straightforward. Okay, so after we learn counting, and then when we get even better at math, so that is when we started doing arithmetic. So how do we add numbers, subtract them, multiply them, divide them, and then we learn kind of fancy ways to do it, like long division, long multiplication, so on and so forth. And then we also start to have a taste of geometry, like study of shapes like circles, squares, triangle, finding areas, and then we step into 3D, finding volumes, so on and so forth. And then using all these ideas, basically you have a taste on how math is applied in real world problems. Things like, for example, if I have $20 now and then I spend $5 on lunch and I bought 5 books at $10 each, how much do I have before? Just a very simple example. Or for example, Mary had 2 apples, John had 3 pears. What is the mass of the sun? But you're not going to see that kind of problem arising. Okay, so with all this, and then when you enter middle school, I think around year 7 or so. So that is when you start looking at algebra. In algebra, that is where things get difficult. It's like a very steep learning curve. It's because instead of looking at numbers, now in math we look at letters. You know how to solve equations, we look at graphs, then we look at funny things like trigonometric equations, we look at exponential equations, so on and so forth. Okay, so doing algebra, it's kind of like a foundation in a calculus. So if you are having trouble with algebra, I don't think you should be watching this video. It's because now I'll be focusing on calculus, which is, like I said, it's a very big step up in mathematics. later on I'll cover like what exactly is calculus, and then of course in calculus it branch out to even more things. And so this is just to give you a rough idea on like where we are going and where we are at with calculus. Of course in the grand scheme I've excluded many like little bits as well, like statistics, probability, fractions, so on and so forth. But that's not what I'm going here. So I'm just giving like a rough idea, like where are we going with this. Right. Okay, so let's have an overview of calculus, like what calculus it's really all about. Okay, so calculus basically just consists of three kind of like three parts. So at its foundation lies the limits. So limits is where we are trying to find the behavior of function when x approaches a certain value. Okay, so it's just like over there, just like a little working that I've done using the limits. And then the idea of limits is basically applied later to study two different things. So one is differentiation. So you can see on the left, that is when you try to find the gradient, the rate of changes of functions. And then on the right, that is where we do integration, finding area underneath the curve. Okay, so those are like typical workings you'll see a lot in calculus. And I mean, I'm doing physics, so I have to use calculus in my everyday life, and I love doing calculus, like every bit of it. Right. Okay, so let's have a look at the limits. So what exactly are limits? So whenever you think of limits, I want you to think of this. The limits is basically we are approaching, but we are never there. You can think of like a guy getting friend zoned by a girl. You can approach her, you can get very very close to her, but you are never there. It's like you're approaching over there. Okay, so now for like a small formal definition, let's just say consider a function like any random function of fx. Could be x squared, could be x cubed, could be 5x plus 3, like pretty much anything. Okay, so when x approaches a number a, like any random number, and the function fx approaches a number l. Okay, so when that happens, we write it as the limit of x approach a fx is equal to l. Okay, so it's just like I'm just like writing it in a mathematical form, like because you do really write the sentence all the time. When x approach a, function approach l, like you don't do that all the time. So we can make it more compact into this little equation right here. So just a very simple example is the line, y is equal to 3x minus 1. So when x approach 2, so when x gets very close to 2, say 1.9999 or 2.0001, so what you find is the graph gets very 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 close to 2. Okay, so I mean, this might seem weird to you, like why do we want to let x approach a number rather than letting x exactly be the number? Okay, so this is the reason is this. It's because very often in math we don't really exactly know what the value of the function is at that point. Like very often it can be undefined. Say example 1 over x, because at 0 the function is undefined. So what instead we can do is find the limit, and so that we can see like roughly like how it approaches, and then we can describe the behavior of the function. Let's also say a very simple example is 1 over x squared. So when x approaches 0, the function approaches infinity. So we say that it just goes up without bound. Okay, so the idea of infinity now makes a lot more sense, in the sense that it keeps going without bound, or it keeps going down to negative infinity. So it keeps plunging down and never like reaching like the lowest point. Okay, so fortunately, like by the use of limits, we can at least meaningfully see like what value the function approaches when x approaches that certain value. Okay, so let's have a look at a very simple yet elegant application of this, which is evaluating pi. Okay, so for those of you who are familiar with geometry, pi is a very strange number with a value of 3.14159265359 and so on and so forth. You don't have to remember the values of pi, just the first few decimal places, it's good enough. And so the pi is basically the ratio between the circumference and the diameter of a circle. Okay, so of course now, how can we actually find the value of pi? I mean, the definition is really straightforward. Okay, so what I'll do is imagine having a circle with a diameter of 1. The circumference over here will be given to be the value of pi. Okay, so I mean, if you want to find the value of pi, one way to do it is you measure the circumference, or take a string, line it up with the circumference, and then measure the length of that string as precisely as you can. Okay, but the thing is, when you do that, at most you can get like 5-6 decimal places, even with the most advanced like measuring instrument. Maybe 8 to 9 if you use like super precise length measurement. But the thing is, in math we are not too satisfied with that, because in math we want to know exactly what the value is. and we want to do better than that. And fortunately, there are actually a few ways to go about doing this, and today I will teach you one way to find the value of pi. Okay, so one way to do it is basically we try to fit polygons into a circle. So if you remember what a polygon is, it's just kind of like a square, a pentagon, a hexagon. Okay, so just like a straight sides, and they're all with equal length. Okay, so if you look at the picture, so if we can fit a polygon into a circle, and we can use this idea to approximate the value of pi. Okay, so if you look at the left, if you fit a square into a circle, it's nothing too impressive. But because you can see the parameter of the square do really reflect the length, the value of pi, or like the circumference. But if you try to fit a hexagon, so now you can see the parameter of the hexagon much closely resembles the circumference of a circle. So in other words, the parameter much closely resembles the value of pi. And then if you use an octagon, the approximation gets even better. So you can see now the parameter of the octagon very closely resembles the circumference. Also, we can expect is this: the more sides we have, the closer the parameter of the polygon will be to the value of pi. And in other words, we can write it in this manner. So the limit of n approach infinity. So when n gets very big, the should get closer and closer and closer and closer to the value of pi. Also take note over here, infinity is not really a real number. It's just saying that, okay, you know what, I let n keep on growing without bound. You can put in 1 million, a billion, or a trillion, just let it keep growing, and then the parameter should slowly approach the value of pi. So of course the next question is this: how can we actually find out what the parameter is? Fortunately, it can be done very easily. So in order to find the parameter of the polygon inside a circle, we first take note of this. Okay, so an n-sided polygon within a circle can be divided into n isosceles triangle with a middle angle given by 360 degrees divided by n. So here are some like the first few values. So if you look at a square, it can be broken into 4 isosceles triangles, and the middle angle is given to be 90 degrees. And say a hexagon, so 6-sided, so it can be broken down into 6 isosceles triangles, and the middle angle, they are all given to be 60 degrees. And finally for the octagon, so with 8 sides, you're dividing the middle angle, like the 360 degrees by 8, so you get 45 degrees, and there are 8 isosceles triangles. And of course, each of the isosceles triangle, they all have a side length of half, because that is the radius of a circle. Because if you look at the sides of the polygon, it's nothing more than the radius of a circle. So now we can make use of these two pieces of information, and now we can apply it to this formula right here. Okay, so this formula is that the base of an isosceles triangle is given to be 2a sine theta divided by 2. So you can see from the isosceles triangle that I've attached over at the right hand side. So say you have the side length to be a, and then the middle angle to be theta, and then when you divide that by 2, you take the sine, and then 2 times of it, you get the base of the isosceles triangle. Okay, so you can show this very straightforwardly by using a trigonometry and using a geometry. Okay, so now what this means is that the parameter of an n-sided polygon in a circle can be given by this formula. So n times of sine 180 degrees divided by n. Okay, so at the front, you don't see any terms over there. It's because the 2 and the half, which is the radius of the circle, cancel out to give you 1, and then 180 degrees, which is just 260 degrees divided by n. Okay, so now we can say that the limit of n approaching infinity of this term right here will give you the value of pi. In the lecture handout, I've tabulated a few values of n. Okay, so you can see when n is equal to 10, this limit right here has a round value of 3.09, so not that close to pi. But as you go to 100, so it's roughly 2.14, so now it's getting even closer to pi, and then 1000, and then now it gets even closer to pi. Okay, so in case mathematicians work out so many digits, decimal places in pi's, basically this is one way you can go about doing it. I mean, what is really impressive is that there's actually a few other more ways to find out the value of pi that involve roughly the same idea. You have something that approximates the circumference of a circle, and then you basically let the limit to go up to infinity, and then you try to approximate your way from there. Okay, so this simple and very elegant example shows why why we want to take limits. It's because infinity is not really a real number. So what we can do, the second best thing is to let n become very big and see roughly what the value of pi is. So technically, by doing that, we can find pi to a very high degree of approximation. I think now mathematicians can easily calculate out the value of pi up to like 1 billion decimal places, which in real life you don't really need that much anyway. I mean, in physics at most we just need like 5 to 6 decimal places, and that's pretty much all we need in practice. Okay, so now let's move on to look at differentiation. Okay, so in differentiation, I want you to, whenever you think of differentiation, the first thing that should come to your mind is rate of change. Like finding like what the rate of change is. Okay, so but the thing is, this term rate of change is also a very common source of confusion when students they first studied differentiation. Like we call it differential calculus. Okay, so now I'll just give you like the formal definition first. So say consider the graph of say y is equal to fx with the following graph. Okay, so now pretend we want to find the gradient at any point given in a graph. So how can we do that? Okay, so one way to do it is by really drawing physically the gradient at that point. So the gradient, it's the tangent of that point. So the tangent is basically the line that touches the graph only one time. Okay, but the thing is, drawing it physically is not very accurate, and I mean in math we want to have like a more systematic way to go about doing it, and fortunately there is a way. Okay, so the trick behind doing this is pick the value of x where you want to find what the gradient is, and then pick h, which is maybe a little bit on the right hand side of the graph together, and then find that gradient. Okay, so what happens if you let the value of h, or the incremental value, to drop down slowly to 0? What happens is the gradient of the secant slowly approaches down to the value of the gradient you're trying to find at that point. Okay, so you can see from the diagram that I've attached over there, say the blue line over there is the gradient you're trying to find, and the red line is the gradient of the secant that you're trying to match it with the gradient of the blue line. Okay, so when h goes down to 0, or what you see is the gradient of the red line slowly approaches the gradient of the blue line. Okay, so that right there is captured in the following limits. So dy dx, which is the gradient of the curve, we also call that the gradient function, is given to be the limit of h approaches 0, and then at the top you take rise over run. So f of x plus h minus away fx, and then at the bottom you divide it by h. Okay, so it's a very simple formula, and it's important to take note that we cannot let h to be exactly 0. Because when we let h to be exactly 0, we get 0 divided by 0, which is undefined. And in mathematics, we don't like to deal with undefined values. So, which is why it's important now that we are taking the limit of h approach 0, but not equal to 0. So that is why limits is really important in the study of differentiation and finding the rate of change. Okay, so of course it's natural to wonder, why do we want to find the gradient of a curve? Like, why do we want to find the differentiation of a function? Like, I mean, because the teacher told us to do so, which not a very good reason. Actually, it turns out by differentiating a function, by finding the gradient function, it tells you a lot about a function. First of all, you immediately know the gradient, so you know where it is increasing, where it is decreasing. It allows us to find the turning point, which is really handy. And okay, so what is but that will not be what I'll be focusing on today. For today, I'll focus more on what exactly does the gradient really represent. Okay, so if the independent variable is time, so if the x in the previous slide is time, and then y is distance. Okay, so usually if we find something, the rate of change of something with respect to time, we are actually finding out how fast that variable is actually changing physically. Okay, so say for example, in the lecture notes I've written, say dx over dt. So say x is distance and t is time. So dx dt, the rate of distance changes with respect to time. So the rate of change of distance. So that is like how fast distance is changing, and that is the speed. Okay, so say dv dt, say v is the volume, and then when you differentiate volume with respect to time, you get dv dt, which is the rate of change of volume. Okay, so you can think like physically like a balloon like expanding out. So dv dt tells us how fast the volume, like how fast the balloon is expanding, and if it is negative, it is pretty much shrinking. Okay, so this is where like a lot of confusion will come in. It's because when we think of rate of change, we think of things like actually changing very quickly. Okay, but what if x is not really the time? but rather it's like some other variable. Okay, so now dy dx will take on a very different meaning, and the term dy dx basically instead tells us how sensitive y is when x changes. Okay, so you can think of it this way. I mean, when you say like a person is emotionally sensitive, so you can say that that person has very high the emotion over the circumstances. So if the circumstances change a little bit, the emotion change a lot. So we call that emotionally sensitive. Same idea over here as well. If you have a very high dy over dx value, it means that if you change x just a little bit, the value of y is going to change a lot. So that is kind of like a measure of the sensitivity. And of course, the term dy over dx also serves a very important purpose. It's because it allows us to approximate the change in y, when x actually changes. We call this the linear approximation, and it's given by this beautiful little formula right here. So the change in y can be approximated by taking the dy dx term over there, and then multiplying by the actual change in the x. Okay, so if you look at the little picture over there, so it's kind of like you have a curve and you have a tangent. Okay, so the term on the left is like actual change in y, and then on the right is like you're tracing the gradient, and then you're using the gradient to find out approximately what the change in the actual value of a y is. And of course, the bigger the value of the delta x, the further away you're going to get away from actual curve. So that is where the approximation breaks down. Okay, so this is actually also where the term of going off tangent comes from. So say you have the actual curve and then you have a tangent. So the further away you get from the tangent, the further away you're going to get from the actual curve. So hence the term like going off tangent. So like someone going off topic. Right. Okay, so now let's have a look at integration. So like on the other side of calculus basically lies integration. Okay, so what is integration? I mean, in English, it means putting things all together. In math, it takes on a very different meaning, but it's kind of related to the term used in English. Okay, so integration basically refers to the process of finding the area underneath a curve. So say you're given a curve, and how do you find the area under the curve? That is, we call it integration. Okay, so one way to find the area under the curve is basically by taking the curve and then you draw like little rectangles underneath there, and the height of the rectangle reflects the value of a function. Find the area of each rectangle and then put everything up together, and then we accumulate that up. Okay, so not a very efficient way to do it, and I mean, and at best it just gives you an approximate answer. So we want a better way to go about doing that, and fortunately there is, which I'll get to soon. Okay, but first, okay, so why do we want to find the area underneath a curve? I mean, it's a very interesting question, because when I first studied calculus, it's like, oh, I mean, cool, you can find area under the graph, but why do we want to find area under the graph? Okay, so I'll use a very simple example to illustrate a use for integration. Finding an area under the graph, and usually the area under the graph, it represents something. It represents something of like some physical significance. Okay, so let's have a look at example at constant speed. Okay, so suppose a car, it travels at a constant speed of 60 kilometers per hour, and it travels for 1 hour. So you can imagine a car, cruising down along the street at a speed of 60 kilometers per hour down in a neighborhood. Okay, so what is the distance traveled? Okay, so for those of you that has done a little bit of math, will definitely know that distance is equal to speed times time. So it's a pretty straightforward formula, and then you can say that, okay, so the car has traveled 60 kilometers. Okay, so now I kind of have a look at this problem from a slight different perspective. Is this? Okay, so another way to look at it is, okay, so what if we draw the speed time graph? So on the vertical axis we have the speed, and on the horizontal axis we have the time, and then we trace out the speed of the car at every single point in time. Okay, so because it is a constant speed, we expect the speed time graph to be a flat horizontal line. Okay, so now the formula distance is equal to speed times times. It's nothing more than your area of a rectangle or formula. Like, because you can see it's just a nice rectangle, and you're just finding the area of that rectangle. Okay, so that area right there is nothing more than your distance traveled. Okay, so why do I want to bring this up? Is because now let's consider a slightly more complicated scenario. Okay, so now consider instead, because in real life, cars don't really travel at a constant speed all the time. Sometimes they speed up, sometimes they slow down. Okay, so when that happens, how can we actually find the distance traveled? Okay, so now suppose the car, instead of traveling at a constant speed, okay, so what if the car travels speed up steadily from 0 to 60 kilometers per hour in 1 hour? Okay, I mean it's not that realistic because usually car speeds up very quickly, but I deliberately chose this number to make things a bit easier to work with. Okay, so if we trace out the speed time graph, it looks something like this. So at time is 0, so at the starting point, the car is not moving. So after 1 hour, so the car slowly speed up to 60 kilometers per hour. Okay, so how can you find the distance to travel? Okay, so the first way to probably do it, or like the most crude way to approximate it is, okay, you know what, pretend the car travel for 30 kilometers per hour for the first 30 minutes. I mean, since after 30 minutes, it travels at a speed of 30 kilometers per hour. So you know what, let's pretend the car, for the first 30 minutes, travel for 30 kilometers per hour. And then for the next 30 minutes, let's pretend, it travels for 60 kilometers per hour. And then find the distance traveled in each time interval. And then add up the distance. Okay, so that corresponds to finding the area of the two rectangles as seen on the right. Okay, so it's a very crude way to approximate it, and probably you're not going to get the actual distance you're trying to look for. So what we can do is we can improve on that. Okay, so what we can improve on that by, instead of saying half an hour time intervals, what about 10-minute time intervals? Say for the first 10 minutes, the car travels for 10 kilometers per hour. And then for the next 10 minutes, it travels 20 kilometers per hour. For the next 10 minutes, 30 kilometers per hour, and so on until it reaches 1 hour and 60 kilometers per hour. And then you find the area of the rectangles in each one of them by using the simple formula. This distance is equal to speed times time. And then you add up all the formula. Okay, so you can keep on improving that and keep on refining it. But instead of saying 10 minutes, what about 1 minute? Say in the first 1 minute, the car travels for 1 kilometers per hour. The second minute, the car travels for 2 kilometers per hour, and then try to find the speed over there. Okay, so you can see that the more you try to divide down, the more tedious the math is going to get. And fortunately, if you really look at the speed the speed time graph and what I'm trying to find, the more you try to shrink down the time interval, the more the area that you're trying to find represents the area under the graph. So what we find over here is that the area under the speed time graph actually represents the distance traveled. So you can save yourself the trouble of having to divide the rectangles into little really tiny bits and try to add everything up, and just simply use the area of the triangle formula, half base times height. Okay, so in case you are wondering, okay, so what the answer should be, it will be 30 kilometers per hour. So half times 60 kilometers per hour times of 1 hour, and that will give you the 30 kilometers. Okay, so this simple example. Okay, so this simple example, it kind of shows something pretty interesting. Okay, so we see that the area underneath the speed time graph represents the distance traveled, and yet on the other hand, the derivative of distance with respect to time, or dx over dt, represents the other speed. Okay, so it's like, is this really a coincidence? Actually, the answer is no. And this right here is that we call it the fundamental theorem of calculus that serves as a very important link between the two. So the previous example is kind of like it shows a link between differentiation and integration. On one hand, we are trying to differentiate and find the area underneath the graph, and then on the other hand, we are trying to find the rate of change. Okay, so it seems that there is a connection between the two, and the connection is the fundamental theorem of calculus, and probably the most impressive and the most amazing result in calculus that really connects the two seemingly separate ideas together. So it states this: the area underneath the graph is basically given by this formula. So say you're given a random graph of fx, and you're trying to find the area from A to B. So when x is equal to A to x is equal to B. So you can have a rough picture by that little sketch I have right there. Okay, so what you can do is, all you need to do is anti-differentiate anti-differentiate the function x to give you capital fx, and then plug in the values of b and a, and then subtract them out above together. So by anti-differentiation basically means opposite of differentiation. So you have a function, you anti-differentiate it, and then when you differentiate it back, you should get back the original function. So which is why there's a second line over here, where if you differentiate the capital F x, you get small fx. So that right there is what we call the fundamental theorem of calculus, and it serves as a link between both of them. So okay, so we can see that after all, integration is nothing more than the opposite of differentiation. Okay, so it actually also says that the area underneath any rate of change graph represents the actual change in the quantity. Right. So like I said, it's okay. So I think that's pretty much it for today. So like I said, there is so much going on in calculus, and in half an hour there is no way for me to cover everything. But nonetheless, I mean, I just give you like a rough understanding of what calculus is all about. And for today's lecture, I try to keep it short and sweet, so you get like the main points, you get the main concepts like down like really quickly. Okay, so for those of you guys who are watching this right now, just want to say a big thank you for watching this. Really means a lot to me. Okay, so for the next lecture, it will be 2 weeks from now. Haven't really decided on what I want to talk about it. So to stay connected with me, just check out my Facebook page. Just give me a like, and if you have already, just want to say I love you guys a lot. And I'll see you guys again the next lecture. So have a good evening.